Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communication Specialist here at the SETI Institute. Welcome to our viewers from around the world. Thank you for joining us. Please let us know where you are watching from. And also welcome into our listeners on the podcast version of SETI Live, available on most podcast platforms. All right, it's a scene we all know from the movies. The scientist runs in and says, "I found an asteroid. It's coming right for Earth. So what do we do?" Sandia Labs is trying to answer that question as best as they can. And today I am joined by Nathan Moore from Sandia National Laboratories to find out exactly what they have experimented on in saving our own civilization, our own advanced civilization. It's important, everyone, from a potentially destructive asteroid. So welcome, Nathan, into our SETI Live, and thank you for being here today.
My pleasure to be here.
So Nathan, let's start. Is this going to be like Armageddon? Are we sending people up? We're going to stick a nuke in the rock and see and blow it to pieces? Is that what we're doing?
Well, that certainly makes good movies. We'd like to do something a little more planned, a little more carefully thought out, and something with a higher probability of success.
Well, the higher probability of success is definitely a key here. So this, again, we've talked about this on SETI Live before, and so some of our regular viewers will be aware that planetary defense is very important, and not just in a saving our lives kind of way, but in a SETI Institute kind of way. One of the factors of the Drake equation is how long do advanced civilizations last? And so in order to understand that, you need to know what the threats are to those advanced civilizations. Some of them come from within, but some of them are external. And one of those, obviously, is asteroids. I mean, the dinosaurs, as I continue to say, did not have an asteroid program. So, look where they're not anymore. So what is your research? What did you figure out here?
So we looked at a way to deflect asteroids using a nuclear device. That's very unique. All the previous work has been focused on, well, can we just knock the asteroid off course by smashing a spacecraft into it, for example? That can be very effective if you have a small asteroid or you have a very long warning time. Why not? That's perfectly legitimate. There are many other ideas out there. Maybe you could blow the asteroid apart. That might work if it's small enough, or you might create a mess by sending shrapnel into our planet if it isn't broken apart very neatly. So there's been a consensus in the planetary defense community that there are some situations where the only recourse might be to use a nuclear device. And it's very powerful. It's the best way we know to pack a lot of energy onto a rocket. So you could get the rocket there. And okay, so then you have a choice. Do you land it on the asteroid like you see in the movie Armageddon and drill it into a hole, try to smash up the asteroid that way? Maybe that would work, or maybe you make more shrapnel. So there's another idea out there called a standoff nuclear burst. And that involves detonating the nuclear device some distance away, maybe a kilometer, a few kilometers, but not on the surface, some distance away. Still very powerful, still gives it a hard push, but not quite as hazardous as just setting it off on the surface. So it's potentially a way to have a more controlled way of dealing with a large asteroid. By large, I mean perhaps several hundred meters in size or larger. You can deflect very large asteroids this way. Or to deal with an asteroid that surprises us by showing up in our backyard without giving us much warning time. It needs a hard push, but you don't want to just break it all apart necessarily. So this is where the idea of a standoff nuclear burst comes in. Now, no one has tested this idea before. You can go to your neighbor. If you're making holiday cookies, you can go to your neighbor and say, "Okay, could I borrow a cup of flour?" Where do you get a spare nuclear device? So and even if you could do this test in space, that's very difficult. So even though the idea had been around for decades, it had been untested. So that's really our contribution. We figured out a way to test this idea of deflecting asteroids. And it works because the main energy coming out of nuclear devices is typically X-rays. and so, well, we know how to make X-rays. We've been making X-rays for a long time, all kinds of, different accelerators around the world. That's something we know how to do. So we have a facility here called the Z machine here at Sandia National Laboratories. We can talk more about how all that works later, but it's the world's largest X-ray machine, basically. And so we could make a very bright burst of X-rays, and we can vaporize the surface of a small asteroid. It's really a mock asteroid. It's very small, about the size of a marble, and we can send it flying. So that's how we tested that concept.
That is really fascinating. So, I was going to ask you, like, this isn't something where you really want to do an actual field test. These are very powerful bursts. This is a lot of energy. So this isn't something that you're going to go, hey, like you said, I'm not going to go borrow someone's, nuclear warhead and try and figure this out. So how exactly does this work in the lab? Do tell us about this Z machine. I've seen the picture of you standing in front of the building. The building is huge. So what kind of device are we talking about here?
It's called a pulsed power machine. And so it's about 100 feet across, several stories tall. And you can think of it like a large battery bank. It stores electricity around the perimeter. And then it releases that electrical energy very quickly, within millionths of a second. That surge of electricity rushes toward the center of the machine and concentrates that electrical energy for a brief moment in time, just nanoseconds. It's producing a stronger electrical pulse than all of the power plants on Earth combined. So when I say it's our world's most powerful pulse power machine, it's actually more powerful than all our other ways of making electricity, but just for a nanosecond.
Yeah. Wow. Okay.
Just for nanoseconds. Yeah. I mean, we don't leave it on because we'd run up the energy bill, right?
Right.
but what that intense concentration of electrical energy lets us do some amazing experiments. The machine's used for all kinds of things, for studying how planets formed and plasmas in outer space. But what we did is we used that concentrated electrical energy to compress argon gas into a very hot plasma, hotter than the center of the sun. And the argon gets so unhappy, those atoms just want to spit out all the energy as fast as they can. So they shoot out X-rays in all directions. So we get this very bright burst of X-rays that expands outward. And we place our mock asteroid in the way of that. And so as those X-rays wash over our mock asteroid, the X-ray burst is so intense that the surface of the asteroid, or mock asteroid, it's vaporized. And that vapor pushing out works like a rocket exhaust. It pushes the mock asteroid in the opposite direction. And so yeah.
Go ahead.
That's the basic mechanism of how our experiment works. It's the basic mechanism of how a real standoff burst would work in outer space.
How many times did you get to perform this experiment? Science being that, like, it has to be repeatable kind of thing. Is this one of those things you got to do more than once, or was it, this is so high energy, we really can only do it one time, so you've got to do it right the first time?
This is not an experiment you can do every day. We spent months planning this experiment that lasted only a few millionths of a second. Everything has to work the first time. And so when it worked, there was no shadow of a doubt that it worked. But we did do it twice, just to be sure.
Okay, good. So there was some repeatability, and it worked both times. So yay. All right. I'm going to take a second to welcome in people from where they're watching, and then we will get right back to this. Let's see. So welcome in from Sweden, from San Francisco. Hello. From Georgia, Chicago. We have New Hampshire, Northern New Jersey, Romania. Wow. Welcome in. Okay. So getting a bit of a global audience going here, which is good because this is a topic that affects us globally. So when we talk about planetary defense and asteroids, we've discovered, I think the current number is still sitting at 99% of the largest asteroids, the big planet killer ones. But that's not to say that we're 100% correct, right? So the DART mission, of course, did what you said earlier. We took an impactor, we threw it at a planet, at a tiny asteroid, and changed its orbit. So we did what we wanted to do. But what you were talking, that, we had to launch that, we had to wait, there was a timing issue. What you're talking about is a much more reactive ability. So, we find this. What kind of timeline is your experiment sort of looking at, and how big are the asteroids potentially involved?
Yeah, great questions. We found most of the planet killers, we think, let's hope. What if one surprises us? That's always a possibility, or changes its trajectory. There's also the so-called city killers. They're only a few hundred meters in size, but hey, if you lose a city, or you could cause devastation over an entire region, an entire state or small country, that's something we should still be concerned about. In terms of reaction time, the kinetic impact and the nuclear deflection option, they both have the similar problem. You want to detect as early as you can. It takes time to get a spacecraft there. What if you don't detect it soon enough and you do need a rapid response? You get more push with the nuclear deflection option, and that's that's the main reason that folks in the planetary defense community realize you need both options. They're legitimate times to use either one, but there could be times when you do need a strong push. Either you have a short warning time, or if we're surprised and a very large asteroid does come our way, let's hope not, but then you have a way to deal with it, and that's very important.
What sort of so you did this on sort of a very small scale, right? So in order to test it, you had to have, as you said, it was the size of a marble. What is the upscaling effect of actually doing this in reality? Like, what kind of for lack of a better word, firepower do we need to make this happen on an actual reality scale?
Yeah, our experiment was very small, the size of a marble. We're really just testing the idea. We're showing that it works. And actually, we showed it works, and it actually works better than we thought. When we we have various models and mathematical formula we can use to scale up and predict what would happen with a life-size asteroid. We made some estimates, and if you consider a very reasonably sized nuclear device, say 1 megaton, and positioned 1 kilometer from a threatening asteroid, we predict you could deflect an asteroid up to 4 kilometers in size. That's probably larger than we actually need. That's a planet killer, and we don't think we're going to have to face a planet killer. You never know. But that gives us some margin. I think that gives us a lot of assurance that we have a way to deal with pretty much any asteroid that's going to come our way.
It's somewhat of a relief. I'm going to welcome in some more people. I've seen some more locations, and we're getting a little bit wider here. So we've got Portugal, Switzerland, New York, and Venice, Italy. So welcome in, everybody. All right. We're talking about using a nuclear blast. Can you give me the term again?
A standoff nuclear explosion.
Standoff nuclear explosion. I love the terminology. It's just it really is what it's what it says on the tin. What is the issue with this that I see from aside from the scalability? But the other issue is we have this thing called the Outer Space Treaty. We're not supposed to, use nukes in space. Does this method get around that? Do you have to change the treaty? What's the standing issue there?
Yeah, I mean, it's impossible to know what decision makers would do in a real emergency. I think the best we can do as scientists is understand the options as best as possible, to understand the limits of nuclear deflection, to understand the limits of kinetic impact, so that we can make the best decision we can. These kinds of decisions sometimes have to be made very quickly. I mean, our society has not been faced with a large asteroid impact coming soon yet, and let's hope that stays that way. But we have had to deal with other kinds of natural disasters on our planet. And I think if there's something we've learned from how to deal with natural disasters is that preparedness is key. The more we can understand in this case, the physics of how all this works and how these technologies might perform on different kinds of asteroids, the better prepared we can be, and the better informed our decision makers would be in a real scenario.
Just kind of on that same note, did you see the movie Don't Look Up, and did it like sort of cause you to kind of be a little bit more scared than before? I'm just curious, because that movie was very striking for me in the, oh wow, so that's kind of how it's going to go.
I'm a realist and a little bit of an optimist, so I try not to pay too much attention to the movies. But
fair enough. I mean, they're movies. They're supposed to be entertaining, and they're supposed to, get a reaction from you. Reality is always very different. So what's the next step in this experiment? Like, what's the next thing you have to do? We've talked about DART, and DART is still in the analysis phase. So now we have another mission going out to see exactly what kind of damage, or changes, I should say, were done to Dimorphos. What is next for you on this sort of experiment?
It's really important to have multiple options, whether that's kinetic impact or nuclear deflection. On the nuclear deflection side, so far we've only examined the response of mock asteroids made of silica. Silica is an important mineral that's found in many kinds of asteroids, but it's just one mineral. We need to study other types of minerals and rocks and understand how effective is this method going to be. That will let us make better decisions, like exactly where should we position the nuclear device. How much warning time do we really need to have? Do we need 5 years? Do we need 10 years? These kinds of they're physics questions, really, but they have an important role in decisions that people would make in a real encounter.
I want to reiterate that one of the things that you pointed out was that we're not under any threat. This is going to happen, and we're coming up with a solution right now. For at least 100 years, there are no Earth-threatening asteroids that will be crossing our path. The closest one, of course, is Apophis. It will not be hitting us, and we are sending a mission to go observe it. That's OSIRIS-REx has been rebranded to OSIRIS-APEX for that purpose. So again, I point out, there is no threat. We're fine. But as you said, we do need to be prepared. What do you think is kind of like highest on your list for that preparation at this point? Like, we're definitely further along than we were, say, 10 years ago, where we didn't know a kinetic impactor would work, and we certainly hadn't tried anything for a standoff nuclear explosion. So what do you think where are we at with the process?
We've really just began tickling the edge of what we can do. This was the first experiment where someone demonstrated you could actually deflect an asteroid with X-rays. I mean, that is just a monumental step in terms of our understanding. But besides understanding how different materials respond, there are questions about what about the shapes of asteroids? What about how cohesive they are? How tightly they're bound together. We're learning more and more about asteroids all the time, and one of the findings, speculations in some sense, but there's also data suggesting that many of these asteroids, if perhaps not even the majority, might be just large rubble piles. If the so-called junkyard of the universe. If that's the case, then it does change our thinking. We might have to be very precise in how we target these asteroids, whether it's a kinetic impact or a standoff nuclear blast. That might change our thinking. So there's certainly a lot to do to try to predict what would happen in a real encounter. And as we learn more about asteroids, we can do experiments like ours to understand how they would respond to the nuclear option. And hopefully NASA will continue doing experiments like theirs to study the kinetic option, and we'll be prepared for anything that comes our way.
I like that. It's a very optimistic outlook, and I always appreciate optimistic outlooks. We do have some questions from the audience, so I kind of want to take some of those and welcome in. Oh, what we've got Maine. and Australia, and Alabama. Okay, so welcome in, everybody. Thank you again. Once again, my guest is Nathan Moore from Sandia National Laboratories, and we're talking about using a standoff nuclear blast to nudge an asteroid out of the way. Before I get to the audience questions, I do have one more thing I kind of wanted to understand. I brought up Armageddon jokingly, and thank you for playing along. But the thing in that movie was that obviously, they went up to the asteroid, they put the nuclear, they actually blew up the rock. Now, why could this be a problem? You kind of mentioned making more shrapnel, but can you sort of explain for our audience what that actually means?
If you have a large asteroid coming in toward Earth and you want to knock it out of the way, in some sense, there's an advantage if it's just one rock. If it starts breaking apart into many pieces, if you can make the pieces small enough, there's perhaps no worry. If you can get the size of the rocks down to a baseball or a marble, they'll probably just burn up in the atmosphere or land harmlessly on the ground, very minimal damage. We wouldn't worry about it. The concern with trying to break apart an asteroid, and by the way, the term for this in the planetary defense community, they call that disruption. Because it's an actual strategy. You could disrupt the asteroid by just splintering it apart. But the concern is, what if that splintering process is not complete, and maybe you end up with 2 or 3 equally sized asteroids that are now they're all dangerous, and now you have 3 asteroids to deal with instead of 1. That could be a much harder problem. What do you do? Do you try to deflect all 3? What if you don't have enough time because you got your first rocket off just in time, but now you have more asteroids to deal with? You might not know where they're going to land. Smaller targets are harder to track, and you might not have the kind of warning time you need to do accurate trajectory calculations. So those are some of the risks with breaking apart an asteroid, and why there's some thinking that if you can give the asteroid a hard push, but not too hard, just kind of find the sweet spot, that maybe that could be the best thing to do, and at least in some situations.
That's a really good segue into the first question that I saw that I really want to kind of toss your way here. Broken Symmetry asks, could multiple blasts be used for corrections and better security of far enough shifts? So could you send up a sequence of these and set them off? I mean, would it be possible to predict that, or are we still sort of that's a theoretical stage, but maybe?
It's certainly theoretical. We've never tried it. We haven't tried that with kinetic impact either. But it is a legitimate consideration. It could be a good way to do this, either with kinetic impact or with a nuclear device. The ideal situation might be you have enough warning time that you could give it a nudge, see if that's enough. If not, you sweep it some more. It's like cleaning your kitchen until you get all the floor completely clean, then you can rest.
Okay, I like that. So possible, but again, more testing is needed in these kinds of things. And this is not something you really want to test when it's necessary.
Yeah, and that's one of the possible advantages of a nuclear approach is we know they're very powerful. So there's a good chance it'll work.
I like that. Again, I like the optimism. I like our planet. I like living here. There is no planet B. Like that's just going to be true. John Hart asks, and maybe you have the answer to this question and you're just off the top of your head, but how many dangerous asteroids are out there? So what do we have on sort of the number of potentially hazardous asteroids? Again, I want to reiterate, there is nothing threatening us for at least a century, but
yeah, it's an important disclaimer, and we're finding new asteroids all the time. Many of them are very small. Of course, harmless asteroids hit our planet every day. We call them shooting stars. The biggest ones, like the one that hit the dinosaurs, the last one was 66 million years ago, so not very frequent. So there's really a whole spectrum of threats out there. The larger they are, the more destructive, but the fewer there are. So if you want to just talk about, say, what are sometimes called the city killer asteroids, the ones that might destroy a city or an entire region, the estimate is roughly perhaps a few tens of thousands of them that might be in outer space. None of them are on a collision course right now, as you pointed out, so that's good. But we are finding them all the time. And it's estimated that, depending on how you count, depending on what size range you're looking at and so forth, it's estimated that we've perhaps only found about half of them. So there's still work to do to find them all. And until you find them all, you certainly want to be prepared to deal with an intruder.
Fair enough. I'm going to welcome in a couple more. I saw Louisiana. Hi, Ron. Thank you for watching as always. And North Carolina. So we definitely got the East Coast of the United States represented, as well as some Europe going on here. So thank you, everyone. Nathan, what is next for you? Like, what is specifically your next aspect of research? Are you going to continue on this, or are you changing gears and doing something else?
Well, I think there's so much we can do to understand the response of different types of asteroids, different minerals. There are more experiments we can do. We can take all that information and we can put it into our computer models and predict what's going to happen in a real mission. There's how hard should we push these asteroids? Is there a point where we can push them too much and maybe they break apart? We need to find that sweet spot. So there's just so much that I want to do, and I won't have time for it all. But thankfully, there are many scientists around the world in the planetary defense community, besides myself, who are also thinking about these questions.
This is very true. We've had quite a few on. As I said at the beginning, the SETI Institute is very interested in planetary defense for the simple reason that, the not so simple reason, we like living. Like that's an important thing to us, but also in understanding the potential longevity for advanced civilizations on other planets. What are the threats that they face, and can we beat those threats? Can we say, like, okay, sure, a city killer hits a planet every so often, but if we have this technology in place, it's not really a threat because we can take care of it. So thank you for all of the amazing hard work, obviously, that you're doing. I have a physics degree. Nuclear physics was not something I really did much with. I am impressed with anybody who is working on it. That is an amazingly complex field. So thank you so much for doing what you are doing to help protect this wonderful planet that we have.
Well, it's my pleasure. Glad to help.
All right. Well, thank you for joining me today, Nathan. It has been eye-opening, but not as uncomfortably scary as I thought it would be. So thank you. I do appreciate your optimism, and I continue to hold out hope that we will have this solved before we need to actually have it solved. Again, thank you, everybody, for watching, for joining us from around the world. Thank you for your questions. We are the SETI Institute, and 501c3 nonprofit working out of Mountain View, California. And we are here because you help us be here. So thank you for all of your support. If you want to continue to support, your bits, your subs, your Facebook stars, your YouTube super chats, all of these things help our outreach. And also you can go to SETI.org/donate now or give now, and you can support us that way too, if you are able to. So thank you again, Nathan, for being here. And thank you, everybody, for watching. And we will see you next week on SETI Live.